Hello. So now we will study the capillary rise. So what happens if we are having a beaker full of liquid, and maybe let's say it's water, and inside that liquid if we dip a capillary tube, you know the capillary, which it's a cylindrical tube open at both the ends. So if we dip a capillary tube into this beaker full of liquid, we tend to see, actually it is supposed to, liquid is not supposed to rise. Liquid should remain at the same level. But what we see, when we dip this capillary, liquid rises. The rise of the liquid we see. Now the thing is, the cause behind that rise that we want to study, and how much rise it will be happening that we want to study. So what we will do, we'll enlarge this portion, and I'm assuming I'm solving it for the rise. The same thing, same process will be happening for the fall also. If I enlarge this much portion, so what we see, if it is a glass and water combination, what we see, this surface which is supposed to be flat here, it does not remain flat, it becomes spherical. And if you remember the angle of contact, the reason for this is the adhesive and cohesive forces acting onto the liquid surfaces. Because of that reason, it becomes spherical, center goes to upper side and the liquid rises there. Okay, so there will be a fixed value of theta c. There will be this fixed value of theta c, and we want to calculate how much rise has happened. So if you see, this surface is not flat. If there would have been a flat surface, in that case the pressure up and down would have been remain same. But since it is not a flat surface, it's a spherical surface, in that case the pressure onto either side will be different. Okay. Onto the upper side, we know the pressure here is nothing but atmospheric pressure. Okay. So we have to calculate what is the pressure below. Okay. So this is. So the thing is, if you see, this is small r. So a small r is the radius of this capillary tube. It is the radius of this capillary tube. We have to calculate the radius of this spherical surface to maintain to make the relationship between the pressure on either side. Okay. So this is the tangent. This tangent is making angle theta c. This tangent is making angle theta c with the vessel surface. If I draw a normal to this tangent, that normal will pass through the center. Okay. This normal is passing through the center. This is a normal to the tangent. This angle is theta c. If I drop a perpendicular onto this line, this angle is theta c. This angle will become 90 minus theta c, and this angle will become theta c. So this point is C. Let's call it A, let's call it B. So in triangle ABC, I want to see this triangle. This is a right angle triangle. In this triangle, this is the radius. This thing is the radius, this radius of the spherical surface. And this thing is small r, radius of the capillary tube. So if I go for the cos theta c, that will be equals to small r upon capital R. Or we can say the capital R, radius of the spherical surface, becomes small r upon cos theta c. That is equation 1. Okay. Now since we have a relationship between the inside pressure and outside pressure, and you see there is only single surface, there is a liquid, there is a air, nothing else. So the formula was P in is equals to P out plus 2T by capital R. That was the formula for single surface, and here also there is only a single surface. Now P in used to be the side where the center used to be there. The center will be on this side, so P in will be on to this side, that is PATM. So in place of P in, I can write PATM is equals to P out is this side. This is. So I'm calling this P dash. This is the pressure here. I'm calling this pressure here as P dash. So PATM is equals to P dash plus 2T upon capital R. This capital R is small r upon cos theta c. Cos theta c. So that will give us the value of P dash, which will be PATM minus 2T cos theta c upon small r. Okay. So here we got the pressure. Now from this point to the bottommost point, this one, The liquid is static in nature and it's the same liquid. So I can make the relationship between these two pressure. I call this as 2 and here I am taking as 1 point. So if I call that point as 2, then P2 will be equals to P dash plus rho g h. H is the height. So this P2 will be equals to P ATM minus 2T cos theta c upon R plus rho g h. Okay. Now if you see point 1 and point 2, there exists a path between point 1 and point 2 and these 2 points are in the same level. Since these 1 and 2 points are in the same level, so the pressure at 1 and 2 has to be same. So P1 has to be P2 and the P1 is open to atmosphere, so that will be equals to P ATM. So if we put the value, then it will be P ATM is equals to P ATM minus 2T cos theta c upon small r plus rho g h. If we rearrange this equation, the h will be equals to 2t cos theta c upon rho g r. Okay, you see that's the height we are getting. So if we dip a capillary inside a liquid vessel, the liquid will rise inside the capillary and the height of the liquid will be equals to 2t cos theta c upon rho g r. Out of these all things, T, rho, G, R, they all will be positive. And you see, there are two types of fluid. For one type of fluid, like glass and water combination, theta C will range from 0 to 90. In that case, cos theta C will remain positive. So H will be positive. And positive H means liquid is rising. And when theta C is from 90 to 180, like in case of glass and mercury combination, cos theta C will become negative. In that case, H will become negative. So liquid will fall with respect to the surface. Okay. So within this single formula, both the cases will be covered based upon the value of theta c. Okay. So here if you see this rise and fall which is happening, the main cause behind this rise and fall is the adhesive and cohesive forces, and we have calculated these using the pressure relationship. So because of adhesive and cohesive forces, ultimately these liquid surface is becoming spherical, and because of that the pressure difference is being generated, and that becomes the cause behind the rise or fall of the liquid. Okay, thank you.